Time for our first talk of the day, and it will be delivered by Barbara Geller and Ansel Sermersheim. Barbara's primary work involves software development for CopperSpice, and that's consulting, product management, and educational trainings. She has been working in the software industry for over 25 years, and her degree is in electrical engineering from California State Polytechnic University, with additional studies towards computer science. She has worked with a variety of companies on custom applications, in addition to developing Windows applications for several vertical markets, including medical billing, transportation, and construction. And Ansel Sermersheim is a consultant specializing in the development of the CopperSpice project, promoting open source and educational trainings. He has been working as a programmer for over 20 years, and his degree is in computer science, also from California State Polytechnic University. And they have both taken part in so many meetings of ACCU, and that was in San Francisco Bay Area, but also in Amsterdam, Munich, in London. And basically they say that if a programmer tells them that something is impossible, they will find a way out. So they're ready to accept your challenge if you think something is impossible, and they'll do it no matter how many variadic templates is required. And I'll tell you a secret. This is the largest room they've ever spoken in. So let's have a big hand for Barbara Geller and Ansel Sermersheim.
Welcome and thank you for coming. Do we have microphones on at this point? So you can hear me at the back? Excellent. Undefined behavior is not an error. And the title of this talk is really important because errors are one thing and undefined behavior is something else. Okay. Oh, now you can hear me. I can hear the echo. Excellent. So let's get going. Oops. I think the microphone has actually broken at this point. Oh. Sorry for the slight delay here while we figure out what's going on. Ah, perfect. Okay. Little technical stuff is always exciting. So as we begin our presentation, we're going to talk about what undefined behavior is, because you can't reason about undefined behavior if you don't have a definition. So we're going to be talking about a lot of terminology. And we're going to talk about why it's not an error. And we're going to give you some ways to look at undefined behavior. Before we begin, we want to tell you who we are. Ansel and I are the maintainers of the CopperSpice project. And CopperSpice is a set of cross-platform C++ libraries. In addition to CopperSpice, we've also developed several other standalone libraries. One of the things I wanted to point out is DoxyPress. DoxyPress is a derivative of Doxygen. So if you're doing documentation, which you should be, then DoxyPress is something you want to take a look at. It documents not just C++, but several other languages in a variety of outputs. And DoxyPress actually uses the CopperSpice libraries.
One of the founding principles of the CopperSpice project is that everything we do is open source. So all of our libraries and projects are available on GitHub and through our download site. And we do our best to use the very latest in modern C++ technology with everything we do.
We did want to mention that as an open source project, although we are the co-founders, we have amassed several people who have joined the product and work with us. If you're looking for an open source project, we absolutely encourage you to take a look at CopperSpice and the various libraries we have and come and join us.
One of the reasons we wanted to give this presentation is because there are many wonderful presentations about undefined behavior, and you should totally watch them. But most of them are written from the viewpoint of a compiler developer, which is really interesting and fun. But then you get done watching it and you say, but how does that actually teach me what I need to know to write good code? Many of them don't. It actually turns out not to be as helpful to study the compiler, to learn about what we need to know as programmers to avoid undefined behavior.
So what do programmers believe about undefined behavior? Well, the compiler should just fix all my undefined behavior. That's not true. It's not going to, and it's not designed to. Hey, undefined behavior, not my job. Somebody else's job. That's not true. As a developer, it is your responsibility to pay attention to undefined behavior. And we're going to explain why you can't do it. You must avoid undefined behavior in your C++ applications. So part of this talk is, what do we need to learn so we can recognize undefined behavior? And then how do we start avoiding it?
So first we need to cover some definitions. These are right from the C++ standard. These are terms that are specified. For example, defined behavior is code which has a single prescribed meaning in the standard. If you have a line of code that says int sum equals 5 plus 2, and at the end of that line, you don't have a variable named sum which contains the value 7, your compiler's just broken.
If there's a printf and it doesn't actually do what a printf is supposed to do, please report it. That's not okay. So defined behavior is a term that says, this is defined to do this thing. And that is actually what it needs to do. Implementation defined behavior, that's a little different. This is code which has multiple meanings. But the compiler has to pick one, and it has to document it. So with implementation defined behavior, you will know on a particular platform exactly what the result would be.
So for this example, we're asking the question, is the size of an int less than the size of a long? Well, that's certainly a reasonable question to ask. It has to be either true or false. And for a given platform, it will be consistent every time you compile your program.
Unspecified behavior, that's a little different. This is code which has multiple meanings, and the compiler can choose one. On every compile, it could change what it does.
So in this example, we're comparing two string literals. And this sort of looks like a string comparison, but it's not. It's actually comparing the address of these two string literals and asking, do they live at the same location in memory? Now, the compiler is allowed to put these in the same location because they are the same contents. But it can choose based on no reason at all. So for any given run of your program, this will either be true or false, but it's completely unpredictable.
Then there's undefined behavior. And this is code which has no meaning. Dereferencing a null pointer, you're lost then. It just doesn't have a meaning. You can't reason through it. Accessing an object after it's been destroyed. Could be interesting, could be nothing. You don't know. So undefined behavior has an actual meaning according to the standard. But its meaning is that code has no meaning.
Now, there's a couple of terms that we wanted to talk about that are not found in the C++ standard. But they're relevant here because this is what we actually care about as programmers. First, there's the idea of a valid error. An error condition is something that might happen during the execution of your program that you didn't want, like some file you intended to read from doesn't exist. That's an error. Or you're out of memory. Maybe you passed an invalid argument to some function that does check its input parameters. These tend to cause things like assertion failures or exceptions, or you get a result code that says this operation failed. The standard also doesn't talk about the idea of intended behavior. I mean, obviously, as programmers, that's what we want. The program did what we hoped it would do. But as far as the standard is concerned, there's no difference between an error and the behavior you wanted. Both of them are just the result of executing your program according to the rules of the standard.
So what is undefined behavior? It is the result of attempting to execute source code whose behavior is not defined in the C++ standard. It is your responsibility to write code which never causes undefined behavior. The definition of a correct program, it's free of race conditions. It's free of undefined behavior. This isn't asking whether some result you're calculating for your client. It's not looking at that to say, did we get the right answer? This is about saying there's no undefined behavior. And the point about undefined behavior is you can't do it. It is your job, and we're speaking in C++, you must avoid it. And that's a really important point, and frustrating to some, because some people say, can I have a little? No, there's no amount you can have. So operations which fall under this umbrella of undefined behavior, you have to get rid of them, no matter what it takes. So let's take a look at a funny and silly example. I have a really good chocolate cake recipe. It's actually wonderful. It's a recipe. And the ingredients are specified in this recipe. The recipe also says if you want to put walnuts in, go for it. You can leave them out, you can put them in, the cake will be perfect. But the recipe calls for 1 teaspoon of salt. And for conversion, a cup of salt is about 50 times more salt. I can guarantee you, if you put in a cup of salt, the cake will be awful. It will just be not a cake you want to eat. But here's the catch. The salt is an error, but this makes the entire cake undefined behavior, not just the salt. And that's why we've chosen this sort of silly example about a cake. Just because the salt is the problem, it is the entire cake. That could be just anything.
The other factor to consider when you have undefined behavior in your program is sometimes it does what you expected it to anyway. If you take this recipe and you substitute soy milk for milk, you will still probably get a cake. It will mostly work. But still you're in undefined behavior because you're outside the constraints of what the recipe prescribes.
Hang on, I'm coming. What's a talk without a little technical problem? So this is about the idea that programmers think undefined behavior, oh, that's easy. We had somebody tell us, I know undefined behavior isn't good, I just won't do it. Fine, I've solved the problem. But it's hard to find. And what about the rare crash? How often have you had a program that crashes once in a while? And you're like, well, I'll get to it later. It's not that big of a deal. It is. Undefined behavior, you need to get rid of it. That's what we're here to tell you.
And this is particularly important if you're writing code that's going to accept untrusted input. If you're writing a web browser or a server or any sort of network daemon, you must ensure your program is free of undefined behavior. The vast majority of security holes that we encounter in the wild are the result of some kind of undefined behavior being present in some system that's accepting unsafe input.
So here's a list. It's not a complete list, but take a look at it. See if you recognize some of the things that you have encountered in your code. Dereferencing a null pointer? Have you done that? Do you access uninitialized variables? These are undefined behavior. This is what we need to start getting rid of. And this list is, like I said, it's a partial list, but it's the very common list.
So these are sort of the top favorites in the undefined behavior world. But if you go and look at the standard, you won't find this list anywhere. It's spread throughout the whole document. So you really need to be familiar with the pieces of it that you're using to know what's dangerous.
For those of you who do template programming and you're used to Asfine, we came up with Ubine. That is, undefined behavior is not an error. We thought it was an interesting name. Because undefined behavior has a very specific meaning. Something which defined as an error, that's not undefined behavior.
One of the ways we like to look at this is an error actually produces some well-defined result. It's an error status, but you can handle it. You can trap it. You can take some corrective action. You cannot handle undefined behavior. By the time it's happened, it's too late. Your program is in an undefined state, and there is absolutely nothing you can do. So there's really three different kinds of things that can go wrong. There's compile time errors. We do that all the time. We fix it, we recompile the program, and we get an executable. There's runtime errors. We have to put in logic to deal with those. And then there's undefined behavior, which you just have to avoid. There is no other option.
If you could back up, thank you. So this example of my vector at 10. So we're saying that we have an STD vector of 5 elements. Calling the 10th element, this isn't something you can do. This is undefined because of the at. Because if you're calling that method, that is undefined behavior. You have to avoid doing that, which means you need to do testing to make sure this doesn't happen.
So one of the ways to look at this question of undefined behavior is to look at the compiler a little bit. And we're looking at the compiler of the future. We call it EC because I'm a really efficient compiler. And I know you're a really good programmer. And so I know you didn't put any undefined behavior in your program. So if I find some, I just know that you didn't mean to do that, so I'll throw that code out because it'll never happen. I'm a great optimizer.
I'm the evil compiler. I see your undefined behavior. I'm going to zero things out. I'm going to get rid of code. I am going to do things you never thought possible. And I am truly evil, and I will surprise you all the time.
So depending upon your point of view, compilers are either evil or efficient. If you understand how they work, they're very efficient. Your code will be great. If you don't understand how they work, you'll be fighting with them all the time, and they'll keep messing up your code. Now, compilers are pretty simple when you turn off all optimization. So when optimization is off, the compiler just literally translates your code exactly the way you wrote it. So undefined behavior usually doesn't manifest in any form. You can't see it because it's really executing your code one instruction at a time in order. But when you turn on optimization, the compiler does a lot more thinking about what your code means. And if there's a section of code that's meaningless, it's discarded. The compiler doesn't have to tell you about this. And there are a lot of fundamental reasons why, in many cases, a compiler couldn't tell you about this because it can't even know that it's done this. So, as a general rule of thumb, if you have code that works when you turn the optimizer off, and it breaks when you turn the optimizer on or upgrade to a new compiler, you have undefined behavior somewhere in your code.
So as a quick recap, we have defined behavior, implementation defined behavior, unspecified behavior, and undefined behavior. And these are 4 different categories. We want to make sure it's really clear to everybody. Defined behavior, that's what you want. Undefined behavior, you need to get rid of it.
And the categories in the middle, you should pay attention to because they might behave differently on different compilers.
So let's take a look at an example. I know it's a little hard to see. This is the point where everybody gets to shout out things because we like the little participation. What's wrong with my function over here? It doesn't return anything.
That is true.
It looks kind of okay, but there's no return statement. This is undefined behavior. What's really going on at the compiler level is usually, not always, but for most of the time, this code will start executing until it finds a return in some other function or method, which may return a bool, may not. The truth is, this happened in some of our code. We knew we were getting some bad results. You've got thousands of lines to look at. You don't even know where it is. We actually stared at it going, that looks pretty simple. I mean, it took us about 10 minutes to realize the return was missing. There are warnings you can turn on to alert you of this. But this is a bit surprising for some people, that it's not just that you get an error. It is that it will find a return line somewhere in the assembly code somewhere later.
Here's an example from some code that we worked on several years ago. So we have an access to an element in a container that's out of bounds. And in this case, we're using operator square brackets, which exhibits undefined behavior if the index is invalid. Now, this is using a version of the QString class from several years ago in CopperSpice. And at that time, QString didn't guarantee null termination. So let's walk through what this for loop does and why it has some interesting undefined behavior. The purpose of this loop is to find a : in the name of a class, because we want to find the actual class name in this string. So we're walking through character by character, and we're looking for a place where the next character and the character after that are both colons. If we find that, we stop, we're done. Except this didn't work. We tried it over and over. We tried debugging it. It just didn't work. The compiler was quite smart here, or evil.
Actually, it was evil. It was quite evil.
This loop has undefined behavior on the last 2 iterations, because on the last 2 times through the loop, you're indexing off the end of the string. So the compiler says, well, if I ever get into the loop, there's certainly going to be 2 last iterations. And since that's undefined behavior, I know you didn't mean that. So the only way this code is valid is if the input string is always empty, so we don't get into the loop. Therefore, the input is always an empty string. Therefore, the output is always an empty string. We're done here. I made your code way more efficient, didn't I?
It was 1 line. It returned empty string. It said, nope, I can never find this. The problem is it's really hard to debug this because you can't just jump inside the compiler and say, what do you do? But we noticed that no matter what input string we had, the output was nothing. Since then, we have changed CopperSpice, we have null termination, we've optimized this, but we learned a lot from this. So this is an indication that the compiler is free to say, I'm never executing this code because undefined behavior couldn't have existed.
Now here's an example to show you how challenging it can be to read the C++ standard just to determine the answer to the question, is this undefined behavior? So here we have a really small program that just declares 2 variables and then compares their addresses. Now, there's a line in the standard that says relational comparison of pointers is only defined if the pointers point to members of the same object or elements of the same array. Are either of those true here? Well, no. A and B are just 2 unrelated variables on the stack. So it kind of sounds like comparing them with a less than operation is undefined. Now, this is kind of weird because comparing them for equality, you definitely should get the answer false because these are 2 different variables. They have to have different memory addresses. Well, it turns out that there's another paragraph somewhere else in the standard that says anytime you compare 2 things and the comparison is undefined, the result is unspecified. So even though it's an undefined result, it's actually just you don't know whether it's going to be true or false. So this program has no undefined behavior. You just don't know what it will return.
This actually resulted in a defect report in the standard. It's a small one, but we're kind of impressed that we were able to actually draw it to their attention that the wording in the standard was a little bit vague.
Here's an interesting example that is from the Clang team. This is a function that simply sums the first n numbers. And so we have a for loop here that just adds up all the numbers from 0 to max. Now, if you compile this with optimization on in Clang, it actually recognizes that this is summing the first n numbers, and it uses Gauss's formula to eliminate the for loop and compute this in one arithmetic operation. So that's kind of neat. The reason the compiler is allowed to do that is because of undefined behavior. Because if you pass too large a value into this function, then the arithmetic would overflow. And in the overflow case, the answer you get from Gauss's formula and the answer you get from this loop are different. So doing that optimization would be a bug. But the compiler knows you will never pass a value that's too large to this function, right? You promised. And if you play around with the constants here, the compiler actually rewrites the formula so that the ranges exactly match the value you should get. It's a very intelligent part of the compiler.
So here's another example which catches a few people. Do thing 6 takes a const reference, nothing that unusual. It does a const cast, and that's the way you would say, I know I received something as a const, but I want to change it, so I'm just going to do that. Looking at this code, there's nothing wrong with it, but there is. It depends on how the original declaration was made. Now, where is that original declaration that is passed to do thing 6? I'm not sure. But if it was declared as const, received as const, it is undefined behavior to const cast this. That is tricky code to me, because now this code is dependent on how it was called, which may be 3 or 4 functions or methods before where I'm at. We've had people say, I do this. I never thought about it. This happens to be undefined behavior.
So this function and the one on the previous slide are instances of an interesting idea. These are functions that have undefined behavior for some inputs. And the question is, how do you document, or do you document, which input values in your functions produce undefined behavior? Because if you have functions like this, you need to. Now, there's another piece of undefined behavior, and this is an example of undefined behavior that occurs at compile time. That's kind of weird. The standard says specializing a type trait that exists in the STD namespace is undefined behavior. And the reason for this is, if this were allowed, I could specialize the isPointer type trait for int and return true. Now I've said that ints are pointers. That doesn't make any sense.
This would not be a good idea.
It's clearly going to mess up all sorts of template code in the guts of the standard library. So this is simply undefined behavior. But no compiler actually diagnoses this. You'll never get a warning on it.
We're not saying that you can't define your own type traits. We're saying you don't want to overload a type trait that's in the STD namespace. So this is an interesting idea. You're writing a program. You want part of A to happen before B. That's why you're writing a program. It has a flow. Something is supposed to happen, then something else. If the compiler just said, I'm just going to throw it all together and do it all at the same time, that's not going to work. You're not going to have the result you're looking for. This idea that things have to actually happen in a given order is the idea of sequencing. And by studying sequencing, now we have a way to reason through undefined behavior. And it's also going to lead to more readable code.
It's also really valuable to understand the concept of sequencing, because if you're ever going to do multi-threaded code, sequencing is very fundamental to understanding atomic operations and synchronization between threads.
Before we actually talk about it, we need to define what a side effect is.
So an expression is said to have a side effect, and this is a generic computer science term. This is not C++. A side effect just means it changes the state of your program in some way. So changing the value of a variable that already has a value is a side effect. Now, in C++, certain things are not side effects, like returning a value. That doesn't actually change anything. It's just a new value that's available.
Slide over here
Or
so they can see the slide.
A statement which declares and initializes a variable at the same time. We don't look at that as being a side effect because the variable is sort of considered to be born with that value. Nothing changed at that point.
So on line 1, how many side effects do we have based on the definitions we've just explained?
Anybody care to shout out an answer?
0? Anyone with 1? I'm not hearing a 1. It is 0.
Good crowd.
Excellent.
You guys are paying attention.
It's 0 because we have a declaration. And doing arithmetic, adding the 8 and the 5, that doesn't make a side effect. So what about on line 2? How many side effects? I'm hearing just 1? 0? So we have 0 and 1.
The correct answer on this is 1. Because var b has some value before we get to this line of code. It's undefined what the value is, but it had some initial value, and now we're modifying it. So there is 1 side effect on this second line.
So let's take a look at lines 3 and 4. So this list here of these 4 things, this is not a partial list. This is actually the complete definition. These are the actions in C++ which produce a side effect. It's only 4 things.
And it's a pretty short list, so you can memorize it. And it's kind of logical. Reading a volatile object is a side effect. That's the meaning of volatile. It means accessing the variable in any way is a side effect. Writing to any object is a side effect. Or doing I/O, that makes sense because something appears on the screen or on a network terminal or what have you. Or calling any function which does one of these. Well, that kind of makes sense. If the function has side effects, then calling it is a side effect.
So how many side effects on line 3? 1?
I hear some ones.
I'm sorry? Unknown? Well, we're assuming that var A was declared on the previous slide. So var A and var B are nice and declared. So by doing this assignment,
We have 1 side effect.
1 side effect. How about line 4? 3. 2. This is fun. Anyone for 0, 5, 12? Okay, good. Just make sure everybody's awake. Does anybody want to shout out how they worked it out? I can see about the first 4 rows, and that's it. So you're saying it's 2?
And there's a modification of var A and a modification of var B, I heard. So you're absolutely correct. We're decrementing var A, that's 1 side effect, and we're assigning a new value to var B. That's a second side effect. The addition of 2, that's not a side effect, and we're not, and that's all there is on this line.
So there's 2 side effects. Okay, so sequence points. A sequence point, this has been around since the beginning in C++. Sequence points are, as I'm going along, things are happening. At this point, everything prior, that's all been done. And I haven't started anything new. So the idea of a sequence point is at a particular point, the compiler knew, that's all done, this is pending. So there's the option in the compiler to rearrange code. And this is why compilers are so darn interesting, is how does it know where it's safe to rearrange code?
So the answer, if you're looking at sequence points, is between 2 sequence points, the compiler can rearrange the code any way it likes, but it can't reorder code across a sequence point boundary. And so this is the way they were defined in the standard. At that sequence point, oftentimes a semicolon, everything before it had to be finished, including all of its side effects, and nothing after it could have started yet. This is sort of a reasonable way to think about programming. And sequence points have been part of the core language. We actually inherited them from C. They're a very old concept. But they're gone.
C++ 11 changed it. It wasn't a good definition. Again, it was inherited from C. So as of C++ 11, sequence points were eliminated from the standard. The term is now sequencing. I do say it with that effect and the ing, because the ing ending becomes really important to that word.
So with the sequencing idea, sequencing is really a set of relationships on the expressions in your program. So we can ask, of any two random expressions, what is their sequencing relationship? A can be sequenced before B, which is the same as saying B is after A. That's reflexive. They can be indeterminately sequenced, which means one of them happens first and then the other, but you can't guarantee which. And then there's unsequenced, which means the execution of these two expressions can be interleaved. Parts of each one can be happening simultaneously or overlapping.
So here's another example. More audience participation. If two side effects or a side effect and a read occur on the same object and they're unsequenced, you have undefined behavior.
Okay, so sequencing is connected to undefined behavior, isn't it?
Yep, that was the idea. Pre-increment. What's happening on this example? Are these undefined behavior? So I heard a no on just A or A and B. So A, that one is defined behavior. Okay, we got a thumbs up.
So by a show of hands, who thinks A has defined behavior?
I'm not sure that's winning.
Who thinks it's undefined?
Who thinks it's undefined behavior? Okay, we have definitely some people that are saying it's undefined behavior. Because we're looking at the number of side effects and whether it's unspecified. Okay?
So let's look at the answer for A.
Problem is it depends on what version of C++.
Before C++ 11.
Yeah. In 03, I know we're standing a little bit in front of the slides, but in 03, it's just undefined behavior.
And
in 11, it's defined.
Because in 03, we didn't have sequencing yet. And the only sequence point is at the very end of this complicated statement. So we have no ordering between the operations. In C++ 11, the pre-increment is guaranteed to occur before the assignment. So this is well defined. And if your compiler doesn't give you the answer 8, it's broken.
So now that you've seen that, how many people think that B is undefined? Not that many. And that it's nice and well defined?
Okay, people are much less sure now.
Oh, yeah, we got everybody a little bit nervous. Well, guess what? It depends on the compiler and the version of C++. And we're going to try to back out here just so you can see the slides. This is a post-increment, and in 03, undefined. This is undefined behavior in C++ 11.
The rule that makes this well-defined wasn't added until C++ 17. So the sequencing section of the standard keeps getting refined as we add new rules to the language to constrain the way the compiler can reorder expressions. So now, in C++ 17, this does have a well-defined answer.
The problem with why this was undefined has to do with the post-increment and the side effects and when they are done. And there are various sections of the standard. If you want to know the exact sections, we can get you that information. It's a lot of very complicated stuff to read. But this is the understanding of it, is that, again, in 11, it is not defined because of the post-increment. They were missing some terminology.
Now, I'd like to take a moment here and mention that this is the reason why you should not write code that is this tricky. Because the behavior on different versions of the compiler will be different. So we're not advocating that you write code like this, but it's important to understand the reason why.
Okay, here's another one. The order of evaluation for passed parameters to a function. This is actually really important. if you take a look at the way this code is written, and again, don't write code like this. We're not advocating it. We are showing this for the purpose of education. Because we have an assignment of var1 from do thing 1. And then notice var1 is passed to do thing 2. To me, this is complicated code to read. And what's the order?
So one place where you get real code that does this sometimes is when you're allocating memory during the call to a function. Don't do this. And here's the reason why. Before C++ 17, this code was flat out undefined behavior because there was no, the evaluation of function arguments was unspecified. So they could be overlapping. So the assignment to var1 could be partially occurring at the same time as you were passing var1 to do thing 2. So that's just undefined behavior. In C++ 17, the order of operations here became indeterminately sequenced. And remember, that means one expression has to happen first, but we're not going to specify which one. So the compiler has exactly two options in this call. It can do the first parameter first, or it can do the second parameter first.
And if the compiler decides, hey, I'm doing option 1, everything's fine, we get the value for var1 calculated, and then it can pass it to var2. But if option 2 is selected, we're back in UB. Now, we had somebody ask us, well, since the compiler knows that option 2 is UB, it'll just pick option 1. Nice compiler. Sorry, I'm quite evil. I'm not going to tell you what I'm going to do, and I don't have to do it to avoid UB, because you promised me, as a C++ developer, you wouldn't have UB. So no, there's no guarantee, there's no settings you can do, Clang isn't going to get better, neither is GCC or any other compiler. In fact, it will probably get worse. So you have to not write code like this, because it's a sequencing problem.
And the reason why this second option is undefined behavior is because we're using the value of var1 before it's initialized. Just thought I'd mention that to make sure everybody got that.
So here's our fun example. Doesn't look very complicated. It's 2 lines of code. There are 5 answers here. I guarantee one of these is the absolute correct answer. The last one is our representation of undefined behavior. So there's a lot of stuff going on. Again, in a code review, nothing that tragic. 4 and 3, I can do that on a bunch of fingers. How is it going to add the 4 and 3? Is it going to get an extra 1 in here, which is possible? And where is it going to save it in the array? I challenge you now to really think about and pick the answer you think is correct. And this is where we take a break.
We just give people a moment to work through this in their head.
Everybody online, take a moment. So you're saying the second one. How many, and if you're not ready, we can wait. How many for the very first one that it will save it in array element 4? Okay, we've got a few.
Votes. What about the second one, element 5? Okay, we've got
percent.
Several more. That was like 10%.
In 6? Okay, you have to vote. Nobody gets out without voting. Is there anybody who feels unsure about this code?
Yeah, show of hands. Who's not sure?
Okay. Well, I think we did our job.
That's a really good reason to turn this down in a code review.
Yeah.
Definitely.
Turn this down, yes. Did we get to the 7?
Who thinks this is undefined behavior?
Yeah, let's go for undefined behavior.
Okay.
I love it.
Excellent. Thank you all for playing.
Thank you for playing. Should we tell them the answers?
Sure, why not?
Okay, so let's go through this. In 11, it's undefined.
And the reason why is quite subtle, because every operator has to have its operands evaluated before the operator can do its job. However, the rule in C++ 11 says the value computations but not the side effects, of the operands to any operator are sequenced before the value computation of the result of the operator, but not its side effects. Now, that was a little difficult to understand, and I know that.
We added the brackets. We added the but not the side effects. We took the liberty in looking at the standard. Here's where you can find it in 11, because that helps you understand what the standard means when it says value computations.
So be aware that there's two different considerations. There's value computations, which is finding out what value something is, and there's its side effects, and they don't always go hand in hand. In C++11, there's no sequencing rule to determine if the post increment on the left-hand side in the subscript operator happens before the one on the right-hand side. So this is undefined.
So it really is understanding that which happens first, the left or the right. So again, C++11 did not have enough in the standard, so it's just undefined behavior. And it's defined in 17.
So in 17, they added two new rules that prevent this from being undefined. The right side of the assignment, including all of its side effects, is sequenced before the left-hand side, which in turn is sequenced before the actual assignment happens. And if you work through it with that order of operations, you'll get this answer. There's another rule that says the side effects inside the square bracket have to be complete before we access the element of the array. That's also important. So these two rules taken together give this expression a really well-defined meaning.
So we have the 4, we add it to the 3, but we're not done with everything. The question then is, do we increment the right side? Well, we have to do it since it's a post increment. We have to do it after the arithmetic. But now that we have these new rules, it has to be done before the left side.
So now we get to the left side. var b now contains the value 5. We use that to index into the array. Then do the increment. So at the end of this statement, var b has been incremented twice to 6, and we've assigned the value 7 to the 5th array element.
But the post increment on the right happens before the post increment on the left. Was that clear? Is anybody thinking this is bad code?
Yeah. Well, there's a really good reason you don't want to do this. Because this is no longer undefined behavior, but compilers will warn about it. Now, technically, GCC is correct here, because it said there may be undefined behavior. But Clang just flat out says there's an unsequenced modification in access to var b. You have undefined behavior. Now, this is kind of frightening because this is in C++17 mode. And so the question is the compiler warning you about something that would have undefined behavior, or is the compiler not actually following the new C++17 rules yet?
So we dug a little deeper, and we found some documentation in GCC. See, I'm really good with that. I made the slides happen. So in GCC, this is some of the documentation. Basically what they're saying is, well, we know you're in 17, and if you accidentally or you decide to compile it pre-17, it would be undefined. Personally, I find this confusing because I said I'm in 17. I want to know, is it undefined in 17?
The truth is, the modern compilers won't tell you that. And you can take any of the examples off of CPP reference that list, oh, this is the thing that's now defined in 17, and you'll almost always get a warning. So while these new rules exist in C++17, in reality, we can't safely use them.
Undocumented behavior is a little bit different. There's no flat map currently in the C++ standard. But we added a flat map into CopperSpice. And it has the effect of basically the API of STD map, so it's a key value pair. It's designed for very small sets of data. We wanted to add a class, much like you would add a class into your application. But this isn't documented. So the question is, how do we get away with adding classes into our programs when they're not documented in the standard? They already thought about this. It's just undocumented behavior. But it behooves you, when you're designing a class like a Q-flat map, make it intelligent, give it a good API, don't introduce undefined behavior, because you're going to have people that are going to be using your classes. So this is the way you extend your applications, something you already knew. But now you know why it's okay for you to add a class, because you're following the rules of extending the language.
The reason we bring this up at this point is because there actually is a statement in the standard. Anything which is not explicitly defined in the standard is undefined behavior. So it sort of sounds like declaring a function or declaring a class is undefined behavior because it's not in the standard. But that's not actually what the standard meant. What they meant is, we are providing a set of tools for you that you can use to define new terms in the language, define classes and methods and functions. When you do so, it's your responsibility to make sure those new entities don't contain any undefined behavior.
So how do you avoid undefined behavior?
Well, as we've shown in some of our earlier slides, you can get compiler warnings on many of these issues. So really, turn on all your warnings and pay attention to them. It's useful to understand at least the high-level shape of the undefined behavior topic so that you know which parts of your program might be a bit dangerous. Try your code on multiple compilers because different compilers will behave differently. You also want to try different optimization options.
And if you're doing a code review and you're having to decide things like our pre and post, change the code. Find a different way to write it. If a code review is too complicated, there's probably something that's incorrect. Ansel and I do pair programming quite a bit. And if you've never done pair programming, I challenge you, find somebody in your office, sit together, maybe have one person, Ansel keeps the standard open, I usually do some of the typing. He likes to surprise me that he's memorized the standard. I kind of know that's not true, but he reads some of the actual syntax for me. But it gives us an instant code review. We don't have to wait 3 or 4 days to find out that we have something bad. If we're sitting there and one of us looks at the code and it's like, that's too complicated. That doesn't make sense. It is very common that I will say, these 10 lines of code look wrong.
And we'll go try the whole process again. So make looking for undefined behavior an explicit part of your code review process. You also need to treat undefined behavior as a critical bug because it can manifest with any behavior at all. So by definition, it is the highest priority bug you can possibly have because your entire program is incorrect. There are also static analyzers that can test for certain kinds of undefined behavior, and these are very useful because as programmers, we tend to make certain categories of mistakes more often. And so these tools can help you find them. There's Coverity. The Clang Static Analyzer is very powerful and open source. And Purify is also available. These are all very valuable tools. But even more importantly are using the sanitizers that are available in modern compilers. Clang has 4 of them. Many of them are available in other compilers as well. And these are tools that actually add checks to your code based on the assumption that you don't have undefined behavior, but maybe we should check at runtime to see if you violated those conditions. And one of the properties of these sanitizers is there are no false positives. So if you turn on address sanitizer and an error is reported, you absolutely have undefined behavior in your program. I mean, it's always possible the sanitizer has a bug, but that tends not to be the case.
There was a time that we thought that the race condition it was reporting, well, how smart is the sanitizer and all the checks? And we were convinced we did not have a race condition. After a couple days, it was quite humbling. We did. We had to change the code. So we suggest that you trust these analyzers and really try to fix what's ever going on.
Some of these are available in GCC, as I mentioned, and I actually heard very recently Address Sanitizer has become available in the Visual Studio toolchain. There's also a product called Valgrind, which is very useful. It's much slower than the sanitizers because it instruments your already built code. But on the other hand, it means you don't have to recompile your program to do this kind of check. So it can be very useful if you have some binary that you can't easily recompile.
We wanted to mention that we have a YouTube channel, and we've done a large number of videos. Somewhere in this list most of these videos are between 10 and 15 minutes. We've done a variety of them. If you're interested in our CopperSpice project, or you just want to go back and study data types, we have a series that's all the way up there in the corner. There's a lot of videos. Please come and watch them. Subscribe to our YouTube channel. Leave us comments, especially if they're nice ones, and ask us questions. We are passionate about helping people understand whether it's CopperSpice or whether it's just C++ in general. And again, these are some of the libraries we've developed. Everything is either LGPL2 or BSD. So if you're not ready to use something like CopperSpice, which is a huge set of libraries, and you just need, a drop-in replacement for STD string that is Unicode aware, CS string is what you can use. So these lower libraries over here, they can just be put into any application. We are C++ 17 at this point. If you want to know what CopperSpice does, Kitchen Sink is a demo that we have. You can build it. We also have pre-built binaries available off of our website. And there are about 30 demos in there that you can play with. Kitchen Sink is not optimized for perfect code. It is optimized to show off the various widgets and the various things that we have in the GUI libraries.
Thank you all for your time. If you have any other questions, we'll open the floor for questions, or if you think of them later, please contact us directly. We're very passionate about making sure that people have the tools they need to write good C++ code.
Thank you.
Barbara, Ansel, thank you very much indeed. Now, if you've got any questions, could you please join us here downstairs, and we will hand you a mic, and then you can ask your question. And in this way, the whole room and people watching online will be able to hear it. Thank you. We've got a volunteer.
Hello, thanks for the presentation.
Thank you.
I wanted to ask about assigning a value to an uninitialized variable. So this is a change of state, but not observable, because you cannot observe a value of an uninitialized variable because it's undefined behavior. So I was wondering why it is a side effect.
Go for it.
That's an excellent question, and I suspect you're referring to this slide.
This slide,
Yeah.
yes.
Where we're assigning to var b down at the bottom, but var b is uninitialized, so it has no meaningful value. The answer is that there are a lot of parts of the standard that would be very awkward if you had to keep track of variables that had uninitialized values to determine whether you had undefined behavior. So for purposes of specifying the language, it's much better to say assignment to a variable is always a side effect, regardless of its current value or lack of having a value.
For correctness in my own code, I would have initialized var b. So again, we're trying to show examples that show sort of the corner cases. But even if we had put int var b equals 0 on the first line, that would have nothing to do with the number of side effects on the 2 plus 6 on the assignment.
Another way to look at this is if var b were not an int, if it were some data type that had a non-trivial constructor, then var b does already have a value. It was constructed. The construction has already occurred, and now you're assigning a new value. So on the first line, This is actually initialization. It will just construct an object in place. But the second one has to default construct an argument and then call the assignment operator. There's actually a different operation that's occurring. That may be another way to look at it.
Thank you.
Thank you.
Yeah, we've got another one.
Hi.
Hey.
You said the UBs are spread all over the standard. Do you know about any archivist, about any active project where the UBs are actually collected and presented, apart from the apart from the UBSEN and own experience of the programmer?
So you're looking for a collection of everything that comprises UB?
Except for the part when they say what's not defined is undefined.
Fantastic project for you. Can you have it by tomorrow morning?
Sure.
Be fantastic.
To give you
the
a
current
series.
standard is over 1,700 pages. Amazingly, C++ 20, we asked them, it's going to be less pages because they're changing the page formatting. Which is hard for Ansel because he's sort of memorized where certain things are. So now he's got to spend a week relearning the page numbers. That's his job.
But as a direct answer to your
Excellent question.
As a good question, and I don't. No, neither of us know of any such list. I mean, obviously, the true list would be an infinite set because it's anything that's not defined. But I don't even think anybody's gone through and tried to compile a complete list. It would be thousands and thousands of entries.
In the slide that we talked about with the pointer, there was a place where we got the standard, a defect report in. That was part of the problem, is something was over here and something was 3 pages later. And it just didn't occur to us to take those and glue them together. So we talked with people from the Standards Committee, and they're like, I think we could have been more confusing. Let's fix that. And in case anybody runs into this with the standard, please submit a defect report. If something is unclear, let them have an opportunity. Defect reports get in a lot sooner. They don't have to wait until a new version of the standard. They can be summarized elsewhere.
So as another answer to your
Thanks.
question, if there was such a list, it would probably be incorrect.
Yeah, or undefined behavior. Yeah.
As far as confusion goes, example 9, the var A, var B, do thing 1, do thing 1, do thing 2.
Yes.
Why the option 2 is UB and not unspecified behavior?
Excellent question.
Go for it.
The reason why option 2 is UB, well, it depends on an assumption that do thing 2 is actually going to use the pass parameter. And under
It will
option...
use the old value.
What's that?
It will use the old value, and that's probably a logical error.
It's not initialized.
var1 has an uninitialized
Sorry.
value.
Uninitialized. No, it's okay.
Sorry, yeah, that's
we're
UB.
very
Sorry.
sneaky.
Now, in theory, if do thing 2 never uses the pass parameter, it would work. But why would you be passing it then?
Okay, thanks.
Thank you.
Any more questions? I think we've got time for one more, maybe. Yeah?
And if more
If
questions
you've
come
got
up,
more, just
yes.
do form a queue so that we don't waste time.
Just
Yes.
didn't see the queue anymore. This is kind of related. And also, do you have any feelings about which things are undefined behavior and not? Because standards is not clear on all of the cases. So one of my things that I have problem with is not so much the referencing the null pointer, but there is a new concept of indirection through a null pointer. So would you say that setting up a pointer to a null pointer and then calling a function on it that doesn't touch anything from the class, is that an undefined behavior or not? This is related because here var1 you said it would be unspecified if you do thing 2 doesn't touch it. So here you have this pointer that's a null pointer and you don't touch it. So it could be a static function, but it isn't declared as such. So would you say it's an undefined behavior or not?
So it sounds like you're specifically talking about calling a method of a class through a null pointer. Yeah, that is absolutely undefined behavior. That does involve a dereference, even if the method never actually explicitly uses anything out of the class.
Okay, could you point me to the place in standard where it says so?
I'll be happy
sorry?
to take that offline.
Virtual.
Yes,
And
because there's actually a
repeat the question.
dereference in the call itself. If you have a pointer to the object, you have to do, PTR, arrow, method name.
So I couldn't find this in the standard, so that's why I'm asking. But we can take this offline.
Yeah, we'd have to look up the exact area of the spec.
It's only 1,700 pages. Give him till 3 o'clock.
And I believe the last question, please.
Yes.
Okay, thank you. You mentioned that reading a volatile is also a side effect considered by the standard. Could you explain a bit why is that?
The reason that reading a volatile is a side effect is because it's actually fundamental to the meaning of a volatile variable. Every read of a volatile requires an access to memory. The idea is sort of that volatile represents an address of memory that might be changed somehow externally to your program, that's not in your control. So that read is a side effect because it has observable effects to the system as a whole.
And do keep in mind that list of 4, we did get that from the standard. So that is defined in the standard as this is what a side effect consists of.
It's actually a really awkward part of the standard that deals with volatile, and there's a lot of work underway to redefine it in a better way. The current definition of volatile is known to have a lot of issues, and watch this space because it will continue to evolve.
Volatile is changing.
Thank you.
Thank you so much.
And coming back to your challenge, you said you were able to solve any kind of problem.
It may be a
any
lot
issue,
of variadic templates, and that's fine, eh?
But from what I gather from what I've heard is that, if you can't, then your ultimate answer is not sure or it depends.
Yes,
which
it
I believe is
depends,
very,
yes.
very clever. We've already had a round of applause, but there were 2 speakers, so let's have another one for Barbara Geller and Ansel Sermersheim.